Hello guys, welcome back to this wonderful course, numerical methods. Today we are on lecture number 6, the Newton's Raphson method. So we're going to look at assumptions, interpretation, examples, and convergence analysis. Alright, so the Newton-Raphson method is also known as the Newton's method. In this method, we are given an initial case which is the root or the zero of a function, and the Newton-Raphson uses the information about the function and its derivative at that point to find a better guess of the root. So the assumptions are f of x is continuous. You need first derivative is known, so you need to differentiate the function and get the first derivative, and an initial case x0 such that the first derivative is not equal to 0, evaluated at that initial case. Alright, so if the initial case is say xi, then the tangent to the curve at that point will give you the next value, your estimate, which is in this case xi plus 1, and this xi plus 1 is closer to your actual value. So as the more you get closer to the actual value, the more these tangents will get closer to this point. So if I take an estimate which is here, the tangent line will be closer to the true value. So Newton-Raphson deals with the tangents to the curve at that point to give you the next estimate. So how was it derived? So we are given xi as your initial case, which is also the root of f of x, and then question, how do you obtain a better estimate of xi plus 1? So using Taylor series, you know that Taylor series with two functions is given by f of x plus h approximate to f of x plus f prime of x h. From this equation, you need to find h such that the left hand side is equals to 0. If I equate this to 0, then my h will be approximate to e minus f over f prime of x. So a new guess of the root is given by, this is your more, h is more like your step size. H is more like your step size. Difference between those two. So is xi plus 1 is equals to xi, the previous one, minus the step size, which is h, which is f of xi over f prime of xi. And then this formula is known as the Newton-Raphson formula. So the Newton-Raphson formula, what you need function, you need the first derivative, you need your initial case, and this first derivative evaluated at your initial case should not be equal to 0. So the algorithm will be for I is equals to 0 to n, and then you write down the Newton-Raphson's formula, and then your end. So if you're implementing this in MATLAB, you need your function in your M file. So your function will be function of f, which is equals to f of x, and this function of f of x is given. So here you define your function, which is f is equals to x cubed minus 3x squared plus 1, and then the function differentiated, so this will be function fp, which is equals to fp of x, which is the derivative of that, which is defined by 3x squared minus 6x, and then you give MATLAB your initial guess to be 4, and then for I is equals to 1 to 5, because you need 4 steps. So for x is equals to x minus f of x over the derivative, and then it will compute the solution for that. However, we need to do this by our calculators, not MATLAB. So let's find let's use the Newton-Raphson in this case. If f of x is x cubed minus 2x squared plus x minus 3 and x naught is equals to 4, if I differentiate this function, remember for us to be able to use Newton-Raphson, you've got assumptions. You need f of x, you need the initial guess, and then you need the first derivative. So if I differentiate this function, I'll get 2x squared minus 4x plus 1. And then the first iteration will be given by x1, which is equals to x naught minus f of x 0, x naught, everything over f prime evaluated at x naught. And this is equals to x0 is 4 minus function f of x evaluated at this x naught. So substitute here by 4, substitute there by 4, substitute there by 4. Satisfy yourselves that you get this value, 33. And then the first derivative evaluated at the x naught. So substitute this one, 4. 16 times 3, 4, 16, 4, which will give you 33 as well. So 4 minus 1, this is equals to 3. Second iteration, we are now computing. So x naught will give you x1 and x1 will give you x2. So for x2, second iteration, we use the value in x1. So this would be x1 minus f of x1 over f prime of x1. So x1 we know is 3. Evaluate the function at 3. So come again to this function. Substitute where there is an x, substitute by 3. 3 times 3, 9 times 3, 27 minus 27 plus 3. No, this one is not 27. 3 squared. 3 times 3, 9, 18. So this will be 9. 9, yes, 3 minus 3 is 0. So this will be 9. And then this one will be substitute by 3 in this derivative. You get 16. So 3 minus 9 over 16, 2.4375, and so on. So for the third iteration, you are using this value, the second one, and so on, using the Newton-Raphson's formula. Make sure you complete and pause the video and complete this whole table using the function on our previous slide. For the first initial value, we have got xk naught, which is given by 4. Then the function evaluated at this point is 33. The function is 33, and then k plus 1 which is 3. So if k is equals to 0, you've got x naught, a f of x naught, f of x prime naught, and then 0 plus 1, which is x1, which is this one, and then x, the error term there is given by x k plus 1, which is 3, minus xk, which is 3 minus 4, which is 1. You continue for all these values up until you 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 satisfy yourself that you obtain all these values. Please attempt this question on your own and complete this whole table. Convergence analysis. So summary of convergence analysis: when the case is close enough to simple root of the function, the Newton-Raphson is guaranteed to converge quadratically. Quadratic convergence means that the number of correct digits is nearly double at each iteration. Problems with Newton-Raphson's method. So if the initial case of the root is far from the root, the method may not converge. So that's problem number one. Newton-Raphson method converges linearly near multiple zeros. In such a case, modified algorithms can be used to regain the quadratic convergence. So when you have got multiple zeros in a short space or intervals, this will converge linearly instead of having quadratic convergence. Hence, modified algorithms can be used. Okay, thank you. I look forward to seeing you on our next lecture.